So just to review some basic terminology, so we're all on the same page. Some of these terms can be kind of confusing or they're misused. Um, Very often, most people are familiar with DEM, a digital elevation model. This is kind of a generic term that's kind of used sometimes loosely and it's used interchangeably. You'll see both DTMs and DSMs referred to as DEMs. A lot of times DEMs is used as a synonym for digital terrain model. But basically DEM is a generic term that's used. DTM and DSM are more specific terms that refer to a certain attribute. So a DTM or digital terrain model is often referred to as a bare earth model. And that example is in this plot on the lower right here is an example of a digital terrain model. So with a digital terrain model, you have your elevation points in blue here, and you have some on the ground, some in trees, some on the roofs. The digital terrain model takes the last return or the ground return. And so it produces this red line here in the ground, and it's sort of a bare earth surface. One point of note is that you can get some odd effects depending on what interpolation methods are used. For example, in this building here, you can see here the surface was extrapolated underneath the building, but sometimes that might just be a section of no data. It depends how the data is processed and what interpolation method is used. By contrast, you have a digital surface model, and that's often referred to as highest hit model. You might see it referred to as that, and that's this example on the top here. You have same scenario, except instead of taking the lowest elevation, you're taking the first return or the highest elevation. And so that you're getting things like the tops of cars, tops of trees, buildings, cell towers. Again, you can get some strange effects in those surface models. Like, for example, here, you might get a point on one side of the roof and another, and the model might just cut it off. So you might get some strange artifacts depending on the density of the raw LiDAR data. The next two terms are synonyms for one another. You might see something referred to as a normalized DSM or a canopy height model. And these are basically the same things, but just different environments. So they're basically a difference between this DSM and the DTM. So you're taking a difference of the tops and the bottoms. And in the forest, this is often a proxy for tree height. So that's why it's referred to as a canopy height model. It's the height of the canopy. But obviously, it's a little bit of a misnomer if you're in an urbanized environment and there aren't a lot of trees. So in those types of situations, you'll see it referred to as a normalized DSM. So you're subtracting the digital terrain model from the digital surface model. In an urban environment, it'd be things like building heights or cell tower heights or power line heights, things like that. The last term is more of a newer thing, is not as common, but is really interesting. Is called a REM or a relative elevation model. And I have a slide about this at the end, and I'll talk a little bit more in detail. But basically, this is sort of removing the general elevation of a river. So it's sort of detrending the river, and it's producing sort of just a localized elevation profile for that river. And so it produces some really interesting graphics, but it also is really useful some analysis. And I'll talk more in detail later on in the talk about REMs. Um, so for the purpose of this talk, we're going to refer to rasters or gridded products as a digital representation of topography or terrain. But obviously, most people are familiar. You're gridding any kind of variable. It could be anything. It could be population. It could be precipitation. It could be number of dogs per square mile. So a raster could be anything. In this case, because we're talking about topography, I'll be referring to it as elevation or topography. Raster format is basically a grid of squares or pixels. And so essentially you're trying to fit a continuous surface to irregularly spaced data so that you have an elevation at regular intervals along a gridded surface. Just another note um, about terminology. Sometimes you might see rasters referred to as 2.5D. They're basically in 2.5 dimensions. This was a bit confusing when I first saw this term. And basically, what this is referring to is that a raster is basically just showing a slice in one layer of of the ground or of in space. It's not really a true three-dimensional representation. So, for example, for a cave, if you were to set up a LiDAR scanner and scan that entire cave and produce a point cloud of that cave, that is a true three-dimensional representation of that cave. You have elevations on the ceiling of the cave, the sides, the floor. So, a point cloud is a true three-dimensional format. Whereas a raster, as you can imagine, is just a slice of one dimension or in an XY space of that cave. So if you're seeing looking at a gridded raster product, you might see the floor of the cave or the ceiling of the cave. So that's why sometimes it's referred to as 2.5 dimensions as opposed to three dimensions. Um, Grid resolution is defined by the width and height of the pixel. The most standard that most people will see is 1 meter pixels. That is what we get at OpenTopography and produce a lot more and more as data has become sort of higher density. We're seeing like 50 centimeter grids as a standard product. Um, and I should mention we don't produce it at OpenTopography, but sometimes we receive it. Some global data sets in particular are not don't have dimensions that are equal in width and height of pixels, especially some of the like data sets that go into the high latitudes, and so they might be latitude dependent. So you might see cell sizes that are like by longitude and latitude, and so they're not actually in equal dimensions. But for simplicity, most of the open stuff at OpenTopography and the stuff we'll talk about today, we're assuming equal pixel dimensions in width and height. So as I mentioned, ultimately the goal of creating a raster is to go from this irregularly spaced data to a regularized grid format. So in this picture on the right here would be what you might see from a typical airborne LiDAR collect, where you have these irregularly spaced elevation measurements. In this plot, they're represented by these like small yellow dots, and you want to create a regular grid from that. And so this is where interpolation and averaging and other algorithms come into play. So in this example here was from a relatively flat area with little vegetation. We had about 5 plus points per square meter. And so you can see this is like 1 pixel dimension, 1 meter by 1 meter. And we want to ultimately average all of those points and assign it to a single grid cell. And so you were fitting a continuous surface to these irregularly spaced points. The reason we do that is just rasters are a little bit easier to work with in terms of raster math and doing other algorithms, and they're also easier to visualize. So for example, here's a visualization of the 1 meter grid. This is a digital terrain model over a meteor crater in Arizona. So there are a variety of interpolation methods. This is a huge field of research. I'm just going to talk about some of the more popular ones that you'd see and some of the ones that are available in OpenTopography. So the three at the top here that are in bold are interpolation methods that are available to users via the OpenTopography portal. Most people are probably familiar with TINs. These are triangulated irregular networks. Inverse distance weighted is also a very common one, and local gridding. And those are all available to OpenTopography. I'll have some slides a little bit later that talk about those more in depth. But people have also probably heard of or used natural neighbor, nearest neighbor, kriging, and splines. I'll talk about natural neighbor and nearest neighbor in the next slides. Kriging and splines are really interesting. They're a little more complicated to use, but they have a lot of kriging in particular is interesting in that not only does it do a good job of interpolation, but it has the ability to sort of find trends within those interpolations and actually extrapolate data out. So outwards of your actual bounds of your data, and it actually does a pretty decent job in some cases. In addition, a lot of the commercial versions of kriging will also produce like an associated error map as part of the process. And so if you see some weird effects in your interpolated surface, you can go to that error map and see if maybe the errors were high in that region, and you can adjust the different parameters. One other point to note that sometimes confuses people is with a lot of interpolation routines, not all of them, but some of them are fitting the surface to these irregular space points, and some of them might not constrain the surface to your actual measured point. So if you went through and sampled your measured data point and your DEM, they might be different. And so with kriging and splines, you have a lot of parameters that you can tweak to sort of constrain that. Obviously, not all interpolation routines do that. Like, so for example, TINs don't because they're connecting actual measured data points, and we'll talk about that in a few slides. But just something to be aware of that all these interpolation routines have pros and cons and lots of knobs that you can turn to sort of change your output. So here we're going to talk about two or three of the more common routines. We're going to talk about natural neighbor versus nearest neighbor versus inverse distance weighted. They're all kind of related and they're very commonly used. I'm going to talk about natural neighbor first because it's a bit the most complicated to explain. So natural neighbor is sort of an area-based weighting. So this is all starts with Voronoi or Thiessen polygons. And so I'll try to explain that hopefully with this diagram on the right. And so for those of you who are not familiar with Thiessen polygons, basically what you're doing is let's say you have your irregular spaced elevation points. That's these points highlighted in green here. And you want to create a set of Thiessen polygons. And so what a Thiessen polygon is that for every point, for any point along this plane, this polygon that you create around each point, that point is closer to the elevation point than any other point. So for example, in this cell here, any point in this polygon is closer to this elevation point than as opposed to like this one or this one. And this is basically creating sort of a sphere of influence for that point based on the whole data set. So, for example, in areas where you might have closer data points, your Thiessen polygons will be much smaller, and so the zone of influence of that point is less because it's surrounded by a lot more points. Whereas something like here in the lower left, where you're sparser, this point is sort of representing a large portion of that data set. Its sort of influence is much larger because there's not as many points. So that's sort of what a Thiessen polygon is doing. And so as part of natural neighbor, you first are creating these Thiessen polygons for your measured data sets. And then let's say you want to get an interpolated data point. And so in this example, this is that black dot in the center. So your first step is you create a Thiessen polygon for your interpolation point. And that's what you see in purple here. And so then as part of the natural neighbor process, you're intersecting your interpolated data points Thiessen polygon with all of the other Thiessen polygons. And then you're weighting it, you're weighting each of those elevation points by how much area intersects how much your your interpolated Thiessen polygon intersects your measured data sets Thiessen polygons. So for example, this data point here has this Thiessen polygon, and it has a relatively small portion of my interpolated points Thiessen polygon intersects that. And so this elevation point gets a smaller weighting when it gets assigned to this. By contrast, this lower point here intersects a large section of my Thiessen polygon for the interpolated area. And so it gets a large weighting, 32% of this elevation will get assigned to this point. And so it's a weighting by area to assign a new elevation point. So hopefully that made sense. Inverse distance weighting is doing the same kind of thing, except instead of weighting by area, it's doing distance. So for each surrounding elevation point, it's measuring a distance to my point that I want to get an interpolated value for, and it weights it by distance. So points that are closer will have more influence and get weighted higher in the final average that gets assigned to the point. And then finally, nearest neighbor is sort of the simplest, and that it's just finding the closest elevation point to my interpolated point and assigning that exact value to the interpolated point. So there's no averaging that happens with nearest neighbor. It's purely assigning the closest point gets assigned that value. This is nice if people are worried about interpolation errors or averaging effects, but it can be a little dangerous if you're dealing with either really varied terrain or if you're dealing with a sparse data set. You could be assigning an elevation value to your interpolation value, and it would really misrepresent the surface. But in general, if you have a highly sampled data set with a lot of data points, nearest neighbor is quick, and it will generally be okay in those scenarios. TINs are, as I mentioned, triangulated irregular networks. This is a vector format of a surface, so it's kind of a mesh and a vectorized mesh where each point is connecting to every other point. It's based on a Delaney triangulation. Um, and this diagram in the bottom right, it's a little confusing, but this is basically trying to visualize how these triangles are created because as you can imagine, there's many different ways you could connect a triangle. In general, the algorithms are trying to avoid any kind of long sliver triangles because that's not really representative of the surface. You can imagine each one of these planes of the triangle is a representation of the surface. It's like a plane on the surface. And so how these tins are generally created is that they're connected in a way such that if you create a circle that circumscribes the three vertices of any given tin, there won't be another vertice, another measured value within that circle. So that's the algorithm and how it's driven to create these sort of triangulated faces. So at OpenTopography, we're actually producing this what we call a pseudo tin. So we use the popular program LastTools on the back end to do our tinning algorithms. And so it's creating a tin. But because we want to output a regular grid, we don't want this vectorized mesh service, although maybe in the future we might want to output that as well. But currently we want to output a regular gridded product. We create that tin from the LiDAR points. And then hopefully you can see this. Then we just lay a regularized grid on top of that tin. And then each of those grid cells was sampling the tin to produce a final gridded product that's based on the tin. So it's sort of like a pseudo tin in the sense that like all the values will be filled in. It's just not in a vectorized format. So next I'm going to talk about local gridding. This is one of the other gridding options that is available to OpenTopography users through the portal. And we'll show this in the demo, some of the different options, but this is basically just a concept of what local gridding is. And so local gridding uses a search radius. So it creates a grid. So here in this example on the right, we have our irregularly sampled LiDAR points in black. And then we have a grid on top of that. And then the algorithm is going through, and in each grid cell, based on your search radius that you specify, it's finding all the intersecting points of that search radius. And then it's doing some statistics on those points and then assigning that point to that cell. You can adjust this grid cell. So let's say your data set was sparse, you might want to increase your search radius so you can make it larger so it'll intersect more data points and do the averaging and then assign that point to that cell. So one nice thing about the local gridding is we also have a null filling option, which I'll talk about, where you can do sort of cell by cell averaging to fill in areas. As you can imagine, there might be portions of your grid where there's no data. And so you can fill that in with a sort of roving window average. So we'll look at this in the demo, but as part of local gridding, you can get a variety of products. You can create a tin, as we mentioned. You can create a mean product, inverse distance weighted. You can do a min, and this one is interesting to me because this data set is actually not a filter data set that was used for these graphics. So you can see this is on the Kaibab Plateau in on the north rim of the Grand Canyon. And so you have this plateau here with lots of trees, and the local grading using the min actually produces a near bare earth model. So basically it's taking for each grid cell, it's finding the data point that has the lowest value and assigning that to the grid cell. So it's in a way a pseudo digital terrain model. If you really wanted a more accurate ground classification, you can go back to this data set, filter by ground, and then run the min algorithm on it, and you would get a real high quality bare earth model. Here's the max value, where it's taking the maximum value for each of the points within a given cell. Here's point count or point density. So this is a nice metric. This is basically just counting the number of points within each cell. So points in red had a higher point density, points in blue have a lower. And here, this is an airborne LiDAR collect. And as we mentioned last week, during these collections, a lot of the modern LiDAR scanners are scanning back and forth. And they're also, so they have a swath width as the plane is flying along. And then they have to overlap those swaths to avoid any kind of data gaps, and also do some swath to swath ground control. And so that's what you're seeing here is the different changes in the swaths, and maybe they flew some cross patterns, and so you get a higher density in some of the areas on this map. And then finally, you can do standard deviation, which is interesting. This should make sense. Again, we didn't filter this data set, so we have all these trees, and so you got a lot of variability on the plateau, so your standard deviation is going to be quite high. You can see the areas on the cliff face where it was bare rock, the standard deviation is much lower because there's not as many trees and vegetation. So I'm going to go through this in the demo, this is the point I mentioned last week, and I just want to hammer home because it's a little bit of confusing to people, is that there's two methods of getting raster data from OpenTopography. You can always dynamically grid from the point cloud directly, and that's the section on the left that I'll go through, and then there's pre-computed rasters. So first, assuming we have point clouds, which we do for most data sets, you can always just dynamically grid from the point cloud. You can create DTMs, DSMs. There's pros and cons to each of these methods. The con on one hand is that you have smaller, because you're gridding right from the point cloud, you're limited to small areas. It's going to be a little bit slower because it's ingesting all that raw point cloud data. But you do have a lot of control over that grid that you're creating. So you can create it at whatever grid size you want. You have no filling options, and then you can visualize and output those grids in whatever format you want. Pre-computed rasters are a lot of our data providers, when they give us their point cloud, they also have created their own rasters. So they've already pre-gridded the data and they want to supply that to us. So we take that and supply that to the user as well. Again, these are things like digital terrain models, digital surface models. Sometimes we get other products like intensity or canopy height models. The benefit of this is that because it's already been gridded, that algorithm has already been run, you can run much faster jobs in much larger areas because it's not having to suck in the entire point cloud and grid it from scratch. The downside is you don't have as much customization available. You're limited by whatever algorithms the data provider used to create those grids. So there's some trade-offs. In both cases, you can do visualizations in custom output formats. So that's available in whichever method you use. One of the newer products that we've made available as raster products is the canopy height model. And I mentioned this little saying here, one person's noise may be someone else's signal, is because a lot of times as geoscientists, we actually want bare earth and the vegetation is actually in the way. But we have a significant portion of members in other communities like forestry or ecology. And for them, they will actually want to measure the forest, and that's their primary signal. So at OpenTopography, we try to make data available, and we try not to limit the data because we never know how our users are going to use the data. And so, for example, in the forestry community, they're interested in things like canopy height, canopy density, canopy cover. This Kaibab Plateau data set that was provided to us from the U.S. Forest Service, which we just looked at, they also gave us some additional metrics that they wanted hosted, and so we provided those to the users as well. And just to tie this in with last week, we talked about waveform LiDAR. Waveform LiDAR is really useful in the forestry community. Just a reminder, like instead of getting a single point from the top of the tree and the mid tree and the ground, with full waveform LiDAR, you're getting a full distribution of energy, so you can do more sophisticated statistics on things like understory, percent of understory, or volume of crowns, things like that. So it's a really powerful tool and useful to the forestry community. So to keep with the nomenclature, we have canopy height models. They could also be referred to as normalized digital surface model. This is an example in Oregon on the right. This is a canopy height model on top of some imagery. In the canopy height model, any darker greens are basically a proxy for taller trees. So those are higher trees. So with a canopy height model, as I mentioned, you need both a DSM and a DTM. You're subtracting those two to create the model. It's basically just a simple raster math operation. A lot of it will be dependent on how accurate your classifications are. Most data sets these days are using more automated classification routines, so the classifications tend to be pretty good. But I just also wanted to mention if there is a data set in OpenTopo and it doesn't have the DSM and DTM created, and you had the point cloud, you could always manually create one yourself by just taking that filtering by first return and filtering by last return and creating your own DTM and DSM. And then once you have that, you can very easily create your own canopy height models. Um, As OpenTopography, as I mentioned, for any of the raster products, you can create these raster visualizations. We had an intern a couple years ago who worked on this and did a fantastic job of revamping our raster visualizations that are available to users. So as part of his work, he created the ability to make hillshades, color relief versions, colorized hillshades, which is basically taking the colorized DEM, making some transparency to it, and overlaying it on a hillshade. And so that's what you're seeing on this graphic on the right, which is showing the colorized hillshade of Mount St. Helens. But you also have things like slope, aspect, roughness. And for all of these visualization products, you can create Google Earth KMZ products. So rasters are useful for visualizations and analytics, but they're also really useful for QA, QC, and I use them quite often for that purpose. So this is an interesting example. It's a case, these plots on the right are a point count or point density. So again, per given cell, it's just counting the number of ladder points it was and assigning that count to the cell. And you could see these sort of um, straight red lines here that are like this is representing a higher point density. And so the users were looking at this and they went back to the data collector and the data provider and they said, what was going on here? And the data provider or the data collector, I should say, mentioned that this was an airborne LiDAR collect and the aircraft hit some headwinds in this region. And so as you again, you can remember the LiDAR is scanning on the ground, and so if the plane all of a sudden slows down, it's really oversampling those sections of the ground, and so that's why the point density is much higher in these regions because these are areas of high winds where much more data was collected on the ground. So it was an interesting QA QC sort of example. Another really sort of more high profile example of doing QA/QC was based on this paper, um, where the authors talk about how initially they thought they found a new fault scarp. And that might be hard to see in this graphic. It's highlighted in these black arrows, but it's this line right here. Initially, they thought this was a new fault scarp, and then they also saw this corduroy pattern here. And this is sort of a very telltale sign of sort of georeferencing errors. So once again, if you can remember, the LiDAR is sweeping back and forth in general, creating a swath, and then those swaths are sort of overlapped as they call it mowing the lawn as you're flying your collection back and forth. And if there isn't proper georeferencing between those swaths, the swaths might not align properly. There might be a slight offset in elevation of those swaths. And so that slight offset, when it gets gridded, results in sort of this corduroy pattern. So this is a very typical pattern you'd see if there's any kind of georeferencing errors. It also turned out that this section of the data set was on two edges of that swath. And we talked about this last week that sometimes edges of swath, because the laser is pointing off angle, you can have higher errors. Most companies will like trim out a lot of the edges of their swath, but ultimately you don't want data gaps between swaths so that you're kind of limited in what you do. But some of the data processing probably could have handled some of these issues. I mentioned I talk about REMs. This is a slide on the relative elevation models. Um, so with an REM, you're basically removing the trend of the river profile. It's often called detrending the river. And this graph on the right will hopefully describe it. The upper plot here is showing the true river profile in blue. And then during certain sections of the profile, you're fitting a slope to that profile, and then you're removing that slope. So you're detrending you're moving out the general trend of the river profile. What you're left with is this plot in the lower right, where you'll see just the sort of localized elevation changes of that river profile of that river. Um, so this is really interesting. It highlights the local river topography. It's really useful for river morphology, modeling sediment transport, and it makes really cool visualizations on top of that. So our superstar intern who did our visualization revamp, he also created this River REM GitHub package. So it's a Python package that you can install. It's available at this GitHub site. It's really easy to work with. You just feed it a DEM, and most of the default parameters will work pretty nicely. Like for example, this plot in the bottom here is a River REM that was output from his software. So I encourage users to check it out and play with it, make some cool visualizations. It's a really nice tool. While we're talking about hydrology and DEMs, I just want another piece about hydro terminology. Well, you often see these two terms that they're kind of confusing. You'll see the term hydro-flattened DEMs versus hydrologically enforced DEMs. And so they're a bit different, so we're going to talk about them here. First, we'll talk about hydro-flattened DEMs. So let me start with this graph on the left. This is showing a DEM that was created with a tinning method. And this DEM has some topography and has a highway system here. And it has a river that's sort of curving through here, as my cursor is seeing. Hopefully you can see that. It's highlighted in this red box here. And then there's a holding pond with water here in this center red box. And you could probably see along the river and even within the holding ponds, these tinning artifacts. So as I mentioned last week, measuring water with LiDAR sometimes can be difficult depending on what LiDAR system you're using. If the water is really clear, you might not get a return. It might just penetrate the water. Or if it's reflective and you're measuring at an angle, the LiDAR pulse gets shot off into space, never returns to the detector. So a lot of times with standard LiDAR collections over water, you might be missing a lot of data. And then when you go to tin that data, again, as we just talked about, tins are trying to create a mesh between all measured values. But if there's no data over the water, those triangles are going to get very long and extend over the water and create these sort of tinning artifacts, is what you're seeing here. And so what a hydroflattened DEM does is it goes along, in this case, like say along the river, and it finds the adjacent valid elevation values and then applies it as a blanket sort of application to that water surface. So I'm just going to click to the next slide, and you could see all along the riverside and along the holding pond, those adjacent valid values were applied as a single application. So you get a flat elevation surface over the water. And I should stress that this is sort of, again, applying a JSON value. So it's not actually measured value. So it's applying a JSON value flatly across the surface. It's purely a cartographic sort of enhancement. It's not showing any measurements over the water. Hydroflattened DEMs are now a standard deliverable for the USGS LiDAR base spec. And the USGS 3-depth DEMs that are available in OpenTopography all have this hydroflattening applied to them. By contrast, we have hydrologically enforced DEMs. So this is a more like process intensive DEM. It's used more for analytics. And what it is basically doing is it's modifying the DEM such that when water models like let's say Tau DEM or Arc Hydro or any other modeling system is applied to sort of model water flow, the DM is modified in a way that water will flow as it would in reality. So you can imagine in this example here, if you were to apply a water modeling to see how water would flow, water would come from these upper reaches here, the higher elevations, and it would probably hit this highway and then just run laterally. And in reality, that's not how this is set up. In reality, in this scenario, there were culverts cut through this highway system. And so, as part of the hydrologically enforced DEMs, analysts will go through and sort of modify the data. So here they put in cuts where there are existing culverts. And so now when those models are run, the water will flow as it would in reality. So you can imagine this is really useful for hydraulic and hydrologic modeling. It's useful, I imagine it's useful for like things like landslide prediction. Department of Transportation is probably really useful in terms of figuring out where to install more culverts or if there's any kind of road undercutting in any areas. So these hydrologically enforced DMs are really useful, but they're just very process intensive to create. Okay, I think this is my last slide, and then we'll go into the demo. Um, this is talking about the global rasters that are available to OpenTopography users. We also call them global and regional because not all of them are global. Some of them are just North America. We have a variety of them. We have about 12 different data sets. We're always adding new ones. I won't go through all of these in this list, but I'll just highlight some of them. Because these are global, most of these are coarser resolution, like 30 meters, 90 meters, things like that. But we do have at the top of the list, one of the most popular ones and probably useful to our community is the USGS 3-depth rasters. This comes in a resolution of 1 meter, 10 meter, and 30 meter resolution. Um, we don't actually host these rasters. We're dynamically accessing them from the USGS. As I mentioned, they are hydro-flattened. And in addition to that, I've noticed bridges and overpasses are removed from these digital terrain models. So it would be useful for doing any kind of water modeling. The second data set here is probably the most downloaded global raster data set in Open Topography. That's the Copernicus data set. It's from ESA, the European Space Agency. It comes in 30 and 90 meters, and it is truly global. It's based on the Tandem X satellite mission's SAR instrument. So this is a synthetic aperture radar based measurement. JEDI here is the one I mentioned earlier. It's a laser altimeter that is on the International Space Station. Because it's on the space station, it's limited by the space station's orbit, so it only has coverage to like minus 52 or 52 south to 52 north globally. And so it has a coarser resolution of about a kilometer gridding. But the unique thing about this product is that they also created a canopy height model. So for forestry applications, it has almost a near global canopy height model, which is really interesting. A new data set that was added, I think, last year is the GEBCO Global Bathymetry and Topography. This data set is interesting because it has bathymetry as well as topography. So over the oceans, they either use satellite altimetry to figure out the bathymetry, or they have sonar along shipping lanes and things like that to get higher res measurements of the bathymetry. Really interesting about this product is they created two versions, one with the ice sheets and one without. So the version without is actually sampling the bedrock topography underneath the ice sheets. Excuse me. I've grouped GEBCO with the other two bathymetry data sets, so the SRTM 15 plus and the GMRT, excuse me, are also bathymetry data sets. These bathymetry data sets tend to be a little bit coarser resolution, about 500 meters. And then lastly, two new data sets that we've made available are polar data sets. These are the Arctic DEM and the reference elevation model of Antarctica, or REMA. So that's the North Pole and the South Pole. These are also available in three different spatial resolutions. You can get them in 2, 10, or 32-meter resolution. These are digital surface models because they're based on the Maxar satellite constellation, and so they're using optical stereo imagery. So those two were also added, I think, within the last year or two. Um, so I think that's the last slide, and then we're going to just go into the demo. So I'm going to stop sharing for now. Well, not stop sharing, but at least go into demo portion. So we're just gonna first talk about accessing those two different raster products. Then we'll show some of the products, and then we're gonna talk about the API at the end. So we'll look at that Kaibab plateau data set. So to do that, we're gonna go to data catalog, and we're gonna search for Kaibab, and we find the data set here. And this is from the data provided to us from the U.S. Forest Service. We have a point cloud version. We also have the raster data, and then they gave us some additional metrics that we also supplied to the users. This isn't normal. Sometimes we'll just get a DTM and DSM, but in this case, they wanted to supply other products, and so we make those available. So first, I'll talk about gridding from the point cloud. So remember that slide, we talked about two different methods. One, you can go directly from the point cloud. One, you can use pre-computed rasters. Here, we're going to talk about how you would what options you would have if you would grid directly from the point cloud. So you'd select an area on the map, and I won't go into these different parameters. We talked about this last week. This is sort of filtering by classification and other aspects of the point cloud. I'm going to focus more on these interpolation methods because this is an introduction to digital elevation models. So your first grading option is to create a tin. And this is that pseudo tin we talked about. Um, so if you check that box, you can specify a grid resolution, which is nice. So you can customize your grid format. We do have limits we had some people that were trying to grid at too small of a resolution, like ridiculously small, like 1 centimeter. We have a base level recommendation of what, given a grid's point density, which is always up here. Here, this point was 15 points per meter, 15.32 points per meter squared. So based on that, we've limited it to a 25 centimeter grid. So we have an algorithm. It's 1 over the square root of the point density. And that sort of dictates what maybe the smallest grid cell you'd want to go that would still be statistically meaningful. Anything smaller than that is kind of not statistically meaningful. But other than that, you can make this as large as you want as well. So you can adjust this grid resolution. And because this is a tin, you can also control the size of those triangles. So if your data set is very sparse and you don't want to see those long triangle effects, you'd rather see no data, you can make this a smaller number, like 20 meters or whatever you prefer, to sort of limit having any kind of really long, irregularly spaced triangle or irregularly shaped triangles. Again, you can output in a variety of formats. You can output in Esri Arc format, GeoTIFF, or ERDS Imagine. GeoTIFF is the standard, and it's pretty standard in any kind of GIS or any other package. Gets really good compression, so that's usually our default output. I recommend sort of sticking with that. Your next gridding method is the local gridding. And so here are the different variables that you can create. And so you have your min, your elevation max, your mean, inverse distance weighted, standard deviation, and point cloud or point count or point density. And so again, for each of these products, it's going through and averaging the points and assigning whether it's the min or the max to that cell, depending on what option you choose. Once again, you can alter your grid resolution, and then you can change that search radius that I showed in the slide. So if you know that your data set's a little sparse, you might want to make this a bit this number a bit larger. The defaults in OpenTopography are generally pretty good, but you can always change them as needed for your own purposes. And then I said I'd mentioned about the null filling. So let's say you wanted to keep your radius smaller and you wanted to just fill in those no datas with an average. So that's what this null filling is doing. So you have three options here. You have 3, 5, and 7. And what that means is this is a 3 by 3 cell boundary around your undefined value, or a 5 by 5, or a 7 by 7. And so when you select null filling, it's the algorithm is going through, and if it hits a cell that's undefined and you had null filling set to 3 by 3, it finds the 3 by 3 cells around that null value, averages it, does an inverse distance weighted average, and then assigns it to that undefined value. And so it's not changing any existing values, it's just filling in any undefined value. It's called a roving window. Sometimes you might see it referred to that. Here's our raster visualizations. You have a bunch of different options. You have a hill shade, color relief. As you select each option, the appropriate menu options will appear here. So when you select hill shade, you'll see the hill shade options. You can change things like vertical exaggeration. You can change the lighting source and the lighting angles or the altitude of the lighting source. Multi-directional hill shade is kind of a new product. It's interesting. It's shading from all different angles, so it produces a really unique product. So with color hill shades, you can apply some of these preset color maps. And then we have slope, aspect, and roughness. You can output these visualizations as either a TIFF or an Erdas Imagine. And what's nice is you can make a Google Earth KMZ for any of these visualizations. So that's really useful to pull into Google Earth. 3D point cloud, I won't talk about. We talked about that in the last webinar. Contour lines I mentioned last week, but I just want to point out one thing relevant to this talk is that you can generate your contour lines. And then if you want just a snapshot, a visualization of your contour lines, you can check this generate visualization. It'll make a colorized elevation plot of your DEM, and then it'll show the contours on top of that. And I'll show this. We'll go through some of these results right now to kind of see what you can expect from all of these different products, because it can be quite a lot. So again, if you're running this job, you put in your email, put in a title if you prefer, and a description for your own purposes, hit submit. The job gets run on our servers, high performance computing, and then you'll get an email back with the results. And so for something like this, I ran a job earlier. This was over the Kaibab Plateau. And the beauty of this is to leverage OpenTopography to create all these products and just let it run in our systems. And then you get an email, and then you just have to download all these products. One point I just want to note is that we don't hold these products indefinitely. So I think we hold them for like 24, 48 hours. So make sure to download the products. Otherwise, you could always just click this modify and resubmit button, and then you could just rerun your job. But just be aware that you might run your job. If you don't download them in a week, we have to clean out our disks so that they don't fill up. So here you have all those products that we selected. Here's your raw point cloud. Here's your DEMs. So this is the two different gridding methods. So you're going to get a tar, a gzip tar for your tin and for your local gridding. So those will be those two interpolation products. So for the local gridding, if you selected min, max, if you selected all, it'll all be in this tar file. So it'll be all your gridded products. And then you're visualizing each one of those products. So then this is the visualization section. So this viz.tin will be all the visualizations of the tin grids, and this will be all the visualization of the local grids. And then finally, your contour will have all your zipped up contour products, the smooth grid, as well as the shape file of or a vector file of your contours. And then you're going to have snapshots of each of those things and your Google Earth file. So your data product page can get quite long, and I just want to just clarify. So again, for your tin, you're going to have your visualizations of each of the products, and then your links to your Google Earth files that you selected. And then for your local gridding, for each of the products, you can have the same thing. So for your min, max, etc. So it can be a lot of products. The job can run longer, but it's kind of nice to get all these products in one shot. Um, and then again, at the end, you'll have your contour, and here's your sort of visualization of the contour um, with the colorized elevation as the base map. So that is example run through of the products that you'd get. And now I'm going to switch gears a little bit and talk about the API. So the API is really popular for developers and programmers who may not want to have the manual process of going through the portal and selecting an area. They want to programmatically access data. And so our information on our API, if you go to our homepage, is under the resources and then developer/API section. And if you click on that, it'll give you some base information about our APIs as they stand today. For the longest time, most of our API was just for global rasters. But a really exciting development we've had recently is we've opened it up to the USGS 3-depth rasters. So you have an API access to the 1 meter, 10 meter, and 30 meter raster products from USGS. We also have a catalog service for the web that accesses our metadata catalog. So if you wanted to sort of do a data catalog search, we have an API for that as well. So I'm gonna just talk about the global rasters for this talk. So to access, we're gonna access the Swagger documentation, which you'll see in a minute is like kind of like a little GUI interface, and is a good introduction for users if you're not so familiar with working with APIs, how to work with them and what the syntax would look like. So you could either click this REST API or this available via Swagger link. And this takes you to the OpenAPI spec, and it shows you the 3 APIs we have. This first one is the global rasters. This second one is the USGS 3-depth rasters, and then the OT metadata catalog. So if you click on this global DEM, you can see we have this little sort of GUI interface, and you can click on this try it out button in the upper right. So if you click on that, it'll let you interact with this, and you're sort of interacting with the API in a sort of a GUI way, which seems counterintuitive, but it's a good way of like learning what the API is about. Ultimately, obviously, with the API, you want to programmatically access. You don't want to have to do any manual intervention. But this is a good way of learning and seeing what the syntax is. So we have a listing of the short names of the global data sets that are available here. And you have a drop down, and you can select which data set you want. So in this case, we're just going to leave all defaults. Here we have the SRTM 90 meter. You enter in your sort of lat and long box. Area of interest, you select your output format. GeoTIFF is the standard. You could also output an ESRI ArcGrid or an ERS Imagine. Here is the API key. There is a demo here. We really need you to use your own API key, and I'm going to show you. We're going to run this, and I'm going to show you how to get your API key. So we do have a demo API. It has limited use. It's for demos only. So here we're going to hit execute. And while this is running, I'm just going to show you how to get your own API key. So obviously, you need to register for an account to get an API key. So once you have registered for an account, you log into your OpenTopography account. It's free. It's very easy to do. Minimal information. And then just select this request an API key. And that will give you your own API key. The other way of doing it is selecting My OpenTopo. And if you click on My OpenTopo portal, it has settings for your own account. One of the settings is getting your API key. And you only have to do this one time. It doesn't expire. It's one API key per account. So once you have your API key, you're good to go, and you can use it however you need. It's free for all users. I should mention with the API keys, this is not intended for users that are going to use this in commercial applications. So anyone using an API key in software that's going to be sold or is using for any commercial applications or is going to be thousands of API calls per day, we do have an enterprise level set of API keys. If you ever need that, you could always reach out to us and we have information about how to obtain those. But for most people, the standard API key should be sufficient. So going back to the Swagger docs that we were just at, you could see I hit execute, and you could actually just download your file directly from here. So this will be the GeoTIFF file, um, and you can pull it into a GIS or do any kind of analysis you want on it. But we also, as part when you run it, it shows you the syntax of how you can use this in your code. So here is sort of the curl command. So if you're using like a bash script or any kind of Unix scripting, you can plug this in, and it shows you the syntax of the API query, or any kind of HTTP request. This is showing you what the API query would look like. In fact, you could select this and just paste it into your browser, and it would um, download the file. So this is showing you the syntax. But in addition, if you want to see like how to do this in Python, if you go to our homepage, we have an FAQ that's a little hard to find. It's at the bottom of the page. If you click on the FAQ and you scroll down to the technical section. And the last one here is how do I download data from the API with Python? And so I've created a little bit of Python code that will do an API call from within Python. So it leverages the requests library. This is what's actually doing the API call. But I've also imported raster IO to plot the data and to also write out a GeoTIFF. So it's a very simple snippet of code. I encourage you to maybe download it and play with it. You're setting up your parameters here. So your area of interest, which is your min-max lat lon, your data set short name, which is listed in the API documentation, your output format, and then put in your own API key here that you've set up through the My OpenTopo. Then you set all those parameters to a dictionary, and then here's the URL to our global API raster, the URL to our global API. And then basically this is the crux of the code here. It's using this request module, feeding in all those parameters, and then the data is returned to the variable R. And so then you have your data. You can do whatever you want with it. Here I just made a little section where you can plot the data. So here this show command is actually reading in that data and plotting it as a colored grid. And then if you want to just write it out as a GeoTIFF, these are your two lines. So you can take that variable R and output it to an actual GeoTIFF locally on your machine. So if you ever want to use it in Python, this is sort of a good place to start in terms to learn how to do that. So sorry, I went a little over. I'm gonna go back to this page and answer any questions you had. Seems like Chris and Chelsea have been working away.
There's been only a handful of questions,
Okay.
so if you have others, we're happy to hang out, even though we are at the top of the hour. So for those of you who came, thank you very much for hanging out, and if you have to move on, thanks. But if not, feel free to ask other questions in the Q&A section. I saw somebody raise a hand and then put it down. Um, in general, if you type your question, that makes it a little bit easier for us to speak to it. Um, questions. Kathy asked a question about contours in feet, which is actually something that is not particularly well supported by OpenTopography at the moment, but is a good suggestion. And I have made a note that that's something we should probably figure out how to do, because I know that a lot of engineering types of applications oftentimes operate in feet, not metric coordinate systems.
Yeah. Yep. Yeah, and we do have
Uh,
the ability. We did have some issues with the version of we had an output format for outputting the contours for CAD, and we had some issues with it, but we've since fixed that. So any people who in the past had issues with that format, it should be fixed.
yeah, there were some issues with the contours not having the appropriate labels, but we have addressed that. So other questions that have been asked, functions not available for users in other regions of the world. That's not entirely correct, actually. Chelsea and I both clarified that in the chat. Just to remind everybody that, the high resolution LiDAR data sets available in OpenTopography generally have a US and New Zealand centric footprint, because in part, these are countries that have open data programs that make these data sets accessible, also a little bit due to funding of OpenTopography and our partnerships. But if you want to look at these kinds of digital elevation model data in other parts of the world, Matt showed a whole list of data sets that we provide access to that cover, in some cases, entirely the whole planet, and other parts, large swaths of the planet. And you can apply all these raster processing, clip the data, create visualizations, create contour lines. All that process is available applied to those data sets. They're just not going to be as high resolution as the LiDAR-based topographic products available in OpenTopography. And then the last question, I didn't entirely understand. Pauline asked a question about which we should use to map assets with coordinates to output files. And so I attempted to answer that, but I'm not sure I fully understand that question. So, Pauline, if you're still around and you want to re-ask, otherwise. So I think that's it.
Yeah. Yeah. Thanks everyone for coming. That just a reminder, next week, Chelsea and Cassie are going to talk about topographic differencing, and it'll be the same Zoom link that you've used for these webinars. So you can just use the same Zoom.
Yeah, and that should be cool. That's a slightly more advanced topic, but talking about how to use OpenTopography's tools to compare overlapping data sets. So looking at multi-temporal data analysis and looking at how we can quantify change in the landscape with these kinds of data sets. And so that should be super interesting for those of you who specifically are interested in this topic or are just interested in seeing some more advanced applications. Definitely come next week.